So we are discussing how to calculate the wavelength of a wave if the spacing between the resonance is given, right? If the spacing between two resonance is given, how to calculate the wavelength of a wave and how to calculate the resonant frequency. That is what we are discussing. So students, if the spacing is given, if the spacing between two resonance is given, spacing between resonance. So this spacing between resonance in an open pipe, closed pipe or a string, any musical instrument, any type of musical instrument, the spacing between two two successive resonance, that is equal to what? That is equal to, very good, lambda over 2, right? The spacing between two successive resonance in any type of musical instrument like open pipe, closed pipe or a string, the spacing between resonance is equal to lambda divided by 2, means half of the wavelength. Okay, so you can solve question number 14. The frequency of a tuning fork is unknown. A student uses an air column at 27 degrees Celsius and find the resonance spaced by 20.2 centimeter. What is the frequency of the tuning fork? Use the speed calculated in the example 2 for the speed of sound in air at 27 degrees Celsius. So the frequency of the tuning fork you have to calculate. You need to calculate the frequency of the tuning fork. A student uses an air column at 27 degrees Celsius. So what is the speed of sound in air at 27 degrees Celsius? 347 meter per second, right? 347 meter per second. And find the resonance spaced by 20.2 centimeter, the spacing between the resonance, right? So I will write spacing between the resonance, that is equal to 20.2 centimeter. The question is to calculate the frequency. You can calculate frequency, students, and you can tell when you get the answer. Yes. Very good. That is correct. 859, right? Or 858.9 hertz. Can you explain how did you solve this question? Yes. Okay. So first you converted the spacing into meter, right? How did you convert the spacing into meter? Okay, you divided this by 100. So 20.2 divide by 100, that is equal to 0.202 centimeter. Okay, very good. That is correct. Then, yes, now it is in meter. Yes. Yes, very good. So you wrote like this, right? The spacing between two resonance equal to lambda by 2. So lambda by 2, that is equal to 0.202 meter. .404 meter, right? Yes. Okay, who is explaining this? Yara, right? Okay, very good, Yara. So you wrote the equation for frequency, right? Frequency is equal to speed over wavelength. Speed we already wrote, 347 meter per second, divided by wavelength you calculated 0.404. When you calculate this, you will get an answer 859 hertz. So 859 hertz is the frequency. Any doubt, students, or do you all understand this very clearly? No doubt. Okay, what about others? Yes, question number 14. This is for question number 14. Any doubt, Meera? Okay, so we will continue. Question number 15. I will erase this. Can I erase? Question number 15. A 440 hertz tuning fork. So here in this question, frequency is given 440 hertz. Tuning fork is held above closed pipe. Find the spacing between the resonance. So in this question, we need to calculate the spacing between the resonance. Find the spacing between the resonance. Yes. We will check that when the air temperature is 20 degrees Celsius, right? So temperature is equal to 20 degrees Celsius in meter, right? Yes. So Ahmad, can you explain how did you find the answer? Yes. Yes. So from the temperature you can get the speed of the sound, right? How much is the speed of sound at 20 degrees Celsius? Very good. 343 meter per second. Yes. Then what did you do after that? Yeah, wavelength equals means you calculated wavelength using wavelength equals. What is wavelength? Velocity over or speed over frequency, correct? So speed how much? 343, right? 343 divided by frequency 440. Yes, how much did you get for the wavelength? 0.77 meter. Yes. Okay, so spacing between the resonance, that is what we have to calculate. Spacing between the resonance, that is always equal to half of the wavelength, lambda by 2. So this will be 0.77 divided by 2. How much? 0.38, right? 0.38 in meters. You got the answer in meters, right? So spacing is equal to 0.38 0.38 meters. If you need the answer in centimeter, you will multiply this by 100. So you will get a 38 centimeter. Yes. Okay, so you write that answer. Okay, you write that answer. Maybe here we didn't round it correctly. That I will check. 343 divided by 440. That equals, yes, that's correct, 0.78, right? We are getting 0.77955. So when you round it correctly, okay? Because 0.779, right? So 0.78 you write. So 0.78 divided by 2, right? 0.78 divided by 2. So it will be 0.39. So 39 centimeter. That's correct. Can we move to the next? Any doubts? Perfect. Okay, so question number 16. Can anybody, can Meera read the question? Okay, so I will erase this. You can do that question, solve the question number 16. Yes. Bugle can be thought of an open pipe if the bugle were straightened out. It would be 2.65 meter long. So the length is given, length of the open pipe, that is equal to 2.65 meter. 2.65 meter, that is the length of the open pipe. If the speed of sound is 343 meter per second, find the lowest frequency, means the fundamental frequency, right? Find the lowest frequency that is resonant for that bugle. So we need to calculate the lowest frequency, F1. We need to calculate the fundamental frequency. 0.015 hertz. Okay, so can you explain how did you get that answer? Yes, correct. Okay, I think there is a small mistake in the calculation. Can you check the calculation? Just recheck the equation and do the calculation again. $64.7, right? 343. Let me check. Yeah, 64.7 is correct. Can you explain, Meera, how did you get that answer? Open pipe, right? Yes. Yes. Okay, very good. So in an open pipe, the first wavelength lambda 1 means the wavelength of the fundamental wave, right? The wavelength of the first resonance or first harmonic, that is L divided by 2, right? L by 2. Lambda is equal to L by 2. Correct, students? Wait. So open pipe, right? Open pipe. No, lambda is equal to 2L, right? Sorry. Lambda 1, that is equal to 2 times the length, right? 2 times the length. Okay, because open pipe will be like this, right? When I draw the open pipe, the first standing wave or first resonance will be opponent must be antinode. So antinode and antinode, right? So this length, this is half of a wave. So lambda divided by 2, that is equal to length of the pipe. Lambda divided by 2 is equal to length of the pipe. So lambda equal to 2 times length. That's correct, 2 times length. So the wavelength of the first wave or first resonance, that is equal to 2 multiplied 2 multiplied 2.65 meters. So we got to the wavelength, we need to calculate the frequency. Frequency, that is equal to speed over wavelength. Speed is 343 divided by wavelength is 2 times 2.65, and the answer is 64.7 hertz. 64.7 hertz. Did you all get the same answer? You got the same answer, right, everybody? What about Usun? Everything perfect, right? Okay, so this is an open pipe. We got the fundamental frequency, and the question B is find the next two resonant frequencies. So for an open pipe, what is F2 and F3? So we got the first frequency, right? We got the fundamental frequency, and the next question B is what is the next two frequencies, F2 and F3, for an open pipe? So for an open pipe, what is F2 and F3? What is how to find the next frequencies? For an open pipe and string, okay, for an open pipe and string, F2 is equal to what? 2 multiplied F1. F3 equal to what? 3 multiplied F1, right? Correct, students? So what is 2 multiplied F1? 2 multiplied 64.7. 2 multiplied 64.7. Yeah, 129.4, right? And the F3, 3 multiplied 64.7. 199.1, right? 194.1. Okay. So for an open pipe and a string, to get the higher frequencies, we multiply like this. F2 is equal to 2 multiplied F1. f3 equal to 3 multiplied f1, f4 is equal to 4 multiplied f1, like that. And if it is a closed pipe, the relationship is a little bit different. If it is a closed pipe, for a closed pipe, if the question is about the closed pipe, how to get f2? F2 is 3 multiplied f1, okay, odd number multiplied. F3 is 5 multiplied f1. F4 is next odd number 7, right? 7 multiplied f1. Okay, done, students? Okay, the next you can read the next paragraphs given. You can read about the sound quality, consonance and dissonance, musical intervals, octave, beats. So read page number 6. Okay, read page number 6. Take 5 minutes. Take 5 minutes and read page number 6. Yeah, okay. So we will start. Yes. Usun, can you explain the like in the page number 6, right? Page number 6. There are two waveform given, right? Pure sound and the sound from a musical instrument, clarinet. Can you tell what is the difference you observe in between that two wave diagram? Yes, yes. So, like for example, in a tuning fork produce one frequency sound, right? The sound with one frequency, and the human voice or in musical instruments, it will produce number of frequencies. So the sound from those will be combination of different frequencies. That is why the sound is more complex or the waveform is more complex. The difference in sound quality between instruments, that is called a timbre, right? Timbre or tone quality. For example, each musical instrument has their own harmonic frequencies, right? Their own harmonic frequencies. Number of different frequencies will be there. So the musical instrument will be producing a sound of combination of these harmonic frequencies or combination of these harmonics. So each musical instrument will produce its own unique sound. Okay, and that unique sound is called timbre, right? That is the quality of the sound. That is called timbre, and that will be different for different instruments. The next is consonance and dissonance. Who will explain what is the meaning of consonance and what is dissonance? Yes. Yes, very good. So for example, if there are number of sounds, right? There are a number of sound with different frequencies like different pitch, and if you are having a pleasant feeling when you hear that mixing frequencies, right, that mixed sound, and you have a pleasant feeling, if the sound is pleasant to hear, that is called consonance, and if it is unpleasant to hear, that is called dissonance. If there are number of sounds, right, with different frequencies, and when you hear that, if it is unpleasant, that's called dissonance, and if it is pleasant to hear, you are happy to hear, good feeling, then it is called consonance. Then next, Reem, can you explain what is musical intervals? The next one, musical intervals. You have the worksheet open, right? Yes, yes, yeah. The next subheading, musical intervals. Very good. So, for example, a musical interval, we call it octave, right? So, two octaves will have a ratio of frequency 1 is to 2. For example, a sound, its frequency is 50 hertz. 50, sorry, a sound, okay, its frequency is 500 hertz. Then if there is another sound, it is 1 octave higher, will have what frequency? 2 times the frequency, right? For example, this is a musical instrument. This musical instrument is producing a sound, okay, a tuning fork or anything. This one is producing a sound. Its frequency is 100 hertz. 100 hertz is the frequency of the sound produced by this object, and this one is producing a sound. Its frequency is 1 octave higher, 1 octave higher than this one. So how much will be its frequency? How much will be the frequency of the sound produced by this one? 1 octave higher means frequency will be 2 times, right? So octave means 1 octave means 2 times the frequency. 1 octave means 2 times the frequency. For example, this we will call object A, which is producing a sound of frequency 500 hertz, and we have object B. This is producing a sound. So for example, it is given that the object B is producing a sound. Its frequency is 1 octave higher compared to this sound, okay, 1 octave higher compared to the frequency of the sound produced by object A, 1 octave. So how much will be the frequency of the sound produced by B? 1 octave higher means, yeah, frequency will be 2 times, right? 2 times higher. So it will produce a frequency of 1000 hertz. Okay. The next, beats. You know the meaning of beat, right? You know the meaning of the beat music, right? Yeah, beats means it is a characteristic, means beats are characterized by the high and low sound, right? High and low sound levels, right? Beat consists of high sound, then low sound, then high sound, then low sound, like that, right? Okay. So how beats are produced? How beats occur? Yes. So beats occur by the superposition of two sound waves. They have nearly equal frequency, right? Nearly same frequency. For example, we have two sound waves, 388 hertz. Okay, one instrument is producing, or one object is producing a sound with a frequency 388 hertz, and another one producing a sound with a frequency 391 hertz. So these two sound have almost same frequency, right, or nearly equal frequency, right? When these two sound waves interfere, they superpose, it will produce beat. Beat means it consists of, beat are characterized by high level sound, then low level, high level, low level, like that. Okay, so what is the frequency of the beat? How much will be the frequency of the beat? Yes. The smallest one, right? Yeah, okay. The difference of these two, so we will take 391 minus 388. How much? 3, right? 3 hertz is the frequency of the beat. So beat frequency is the difference in frequency of the two individual sound. For example, if you do 388 minus 391, you will get a minus, but don't write a minus, okay? Absolute value of the difference in frequency. So it will be beat frequency always positive, don't write negative, you will get always positive value. Okay, so we will discuss the question, students. Okay, I will give you time. Okay, I will give you 5 minutes to answer Question number 17, 18 and 19. 17, 18 and 19. Okay, 3 questions. After 5 minutes, we will discuss these 3 questions. Question number 17, 18, 19. These are the questions from the textbook.
paper
Yes. Okay, let us discuss, students. Question number 17. What is the vibrating object that produces sounds in each of the following? First one, in a human voice. B, in a clarinet. C, tuba. And D, violin. Yes. So in a human voice, what object vibrates to produce sound? To produce vocal cord. So your answer here is vocal cord. Very good. Vocal cord. In clarinet, what vibrates to produce sound? You can refer your physics book. What? It's called reed, right? Okay. In tuba, lips of the player, right? Yes, good. Lips of the player. Then in violin, correct? String vibrate, right? String vibrate to produce sound in violin. Question number 18. Resonance in air column. Why tuba? Why the tuba from which tuba is made? Why is the tuba from which tuba is made? Oh, sorry, why is the tube, right? Why is the tube from which tuba is made much longer than that of a cornet? Yes. See, they are musical instruments. Okay, you can just write in Google and press image, so you will know the what is it. Okay. So musical instruments, you know, like with that pipe and all, like in your school band is there. You must have seen band, right? So they take these type of musical instruments and just write in Google, then press image, tap on image, you will see that. So why is tuba from which tuba is made longer than that of cornet, right? So the tube of tuba, tube, tube, not like this, but I just want to show you the length. So this I will draw shorter. Okay, this one is longer. Question, why longer? This one is shorter. Question, why shorter? Listen students, if the length of the tube is longer, what about the wavelength? Will it be higher wavelength, large wavelength, or small wavelength? Longer tube means longer wavelength or shorter wavelength? Longer tube, very good. Longer tube means longer wavelength, right? Longer wavelength. I will write longer tube means longer wavelength or large wavelength. Okay, I will write like that, longer wavelength. Longer wavelength. Longer wavelength means what about the frequency? Large frequency or small frequency? Small frequency, right? Longer wavelength means small frequency. Smaller frequency means low frequency. Okay, instead of smaller I will write low frequency. We say low frequency sound, right? Low frequency. So this instrument, tuba, right? Name of the instrument is tuba. Tuba is designed for what? Designed to produce what type of sound? It is designed to produce low frequency sound. Its duty, its purpose is to produce low frequency sound. So how can we make an instrument that produce low frequency sound? By increasing the wavelength, means by making the tube longer, right? By making a longer tube. So they will make like this, then turn like this, then turn like this. To make it longer, they turn it, right? Yes. So what must be the purpose, the duty of this instrument? Yeah, this its purpose, its duty is to produce high frequency sound. Its duty is to produce high frequency sound. So high frequency sound, to produce high frequency sound, what should be the wavelength? Low wavelength, right? Smaller wavelength, shorter wavelength. Okay, anyway, I will write smaller wavelength. Smaller wavelength means it will produce high frequency. How do we know smaller wavelength will produce high frequency? That we know from this equation. Frequency that is equal to speed divided by wavelength, right? Longer the wavelength, shorter the means lower the frequency. Low means large wavelength, small frequency. Small wavelength, large frequency, high frequency. Okay students, I hope you understand this. So we have completed question number 17 and 18, right? 17 and 18. Any doubt? Okay, so we will continue from question number 19 in the next class. Thank you for joining the class, students. Can I end the meeting? Do you have any question? Okay, bye.